Hello, nice to see you. Again, Mr. Johnson, a science teacher. I've been teaching now for about 10 years, and I am going to give you a lowdown today on the periodic table and its development for Key Stage 4 chemistry. You will need a pen and paper, or pencil and paper, just for making notes of your own. Other than that, nothing else is required for this particular course. Okay, so we'll get started. I'm going to share my screen with you so you can see the presentation. There we go. Let's move this down out of the way. Okay, so chemistry, periodic table of the elements. It's a massive part of your GCSE chemistry, and the development of it is usually the bit that most people struggle with, just simply because of the way that it's taught within the GCSE syllabus. So, prior knowledge you should have. From Key Stage 3 chemistry, you should recall the definition of an element, compound, and mixture for this point. Recall and identify some properties of metals and non-metals and their general position in the periodic table. And recall that Dmitry Mendeleev designed an early periodic table with elements in groups and periods. If not, when you finish this, I recommend that you go and just check these things out. Today, though, the first thing we're going to do is describe how Mendeleev arranged the elements known at the time into the periodic table using prior ideas of previous sciences. This is the modern periodic table. You'll be familiar with it. You'll have seen it probably on your chemistry classroom wall. It's common in all science classrooms worldwide. The names and symbols of the elements are internationally recognized. It doesn't matter whatever country you're in, they'll all be the same. How did we arrive at what is such a universally recognized table? And how do we know then that this is actually the correct arrangement for the periodic table? Well, Mendeleev was not the only person trying to come up with a periodic table, or even just a system of classifying the elements. There were other scientists involved, and a couple of those scientists who made contributions to the modern table that we know today are Johann de Bruijne and John Newlands. What they contributed then? De Bruijne developed what's known as the law of triads. Basically, he noticed that some groups of 3 elements had similar chemical and physical properties. So, for example, chlorine, bromine, and iodine, and sodium, potassium, and lithium. Because he was looking at these in groups of 3, he noticed that they had similar chemical physical properties. He started grouping them together. Newlands studied a lot of music theory and he developed what was called the law of octaves. Newlands put the elements in order of their calculated atomic masses at the time. He showed that every 8th element had similar properties. On the left, de Bruijne's triads are present, so you've got the elements lithium, sodium, potassium. You can see their atomic weights as they were known, 7, 23, and 39. You've got calcium, strontium, and barium with 40, 88, and 137. And then chlorine, bromine, and iodine with 35.5, 80, and 127. Newlands arranged elements in octaves are on the right-hand side, and you can see a kind of structure forming, this idea of putting the elements into an arrangement based on what they knew about them at the time. What went wrong though? Well, for de Bruijne's idea, most of the elements that were known about at the time didn't fit into a triad with any others. He couldn't put all of the elements that were known into groups of 3, or even match them into an already known group of 3. So the idea wasn't accepted as correct. Newlands, well, he postulated that every 8th element was similar, but actually it wasn't always correct that every 8th element had similar properties. It was a pattern that he could see, but wasn't true for everything. Not all the atomic masses had been calculated correctly at the time, and the thing was, Newlands didn't leave any gaps from discovered elements. It was kind of an arrogance around the time, I believe, that people just thought there was nothing left to discover. So sometimes he put 2 elements into one box into his periodic table to make them fit. This meant that his idea was not accepted as correct by his peers in the scientific community. So what did Mendeleev do? Mendeleev was really keen on a game called solitaire, or patience. He used the idea behind that to help him arrange what he knew about elements to try and build some sort of structure, some sort of table of the elements. So he wrote down all of the 63 known elements at the time on playing cards. On each card, he listed that element's atomic mass, atomic number, and the known chemical and physical properties. A bit like Top Trump's card game nowadays, but element style. This was Mendeleev's game of cards, and you can see now that you've got the lithium, sodium, and potassium going down the screen on the left. So that's the triad rule that De Bruyne noticed. And 2, 4, 6, 7 going along. So this idea of Newlands, but instead of 8s, it seems to be 7s. He realized after messing around with them that he could arrange the elements such that patterns would emerge in the physical and chemical properties then, just like De Bruyne had said. And it was repeated every 7 elements, like Newlands had postulated, but not with 8. The genius of Mendeleev was that, unlike the rest, he left gaps if the element didn't fit. He basically simply assumed that the element, if it should be in the gap and hadn't been discovered yet, leave the gap there for it. It was an idea that hadn't seemingly occurred to De Bruyne or Newlands. Leaving gaps then meant that Mendeleev was able to position the existing known elements so that vertical columns contained elements with increasing relative atomic mass, and horizontal rows contained elements with similar chemical properties. This is Mendeleev's periodic table. It looks slightly different to ours because his vertical columns contained elements with increasing atomic mass, and horizontal rows contained elements with similar chemical properties, but we've inverted that in the modern periodic table. So Mendeleev arranged the elements known at the time into the periodic table using the ideas that we've discussed from De Bruyne and Newlands. But how did Mendeleev predict the position and properties of unknown elements and the problems that came out through his approach? A big part of science is once you ask questions and you seem to find the answer, you need to be able to test that answer. To do that, scientists make predictions. And if you can predict what's going to happen with the answer that you've got correctly, and 9 times out of 10, the theory is accepted as valid. Mendeleev's periodic table in 1980-72 looked like this. These were all the known elements at the time. The metals are the ones shaded in orange. The non-metal elements are shaded in blue. Red boxes were gaps that he left for elements that hadn't been discovered at the time, but that he thought should exist based on what he'd done with the patterns. This gave Mendeleev the opportunity to make then predictions about the properties of these unknown elements. He used the patterns in the properties of the elements around them to make his prediction. So for example, the box, the red box, in series 4, group 3, which has the atomic mass of element 44, he used the patterns in boron, aluminium, and deuterium in the group above and below it to help make predictions about what was occurring there. One set of predictions that he made then was for the undiscovered element 68, which he called Eka aluminum. Now, he predicted that Eka aluminum should have a relative atomic mass of about 68. It should have a density of about 6.0, a melting point which was quite low. If it reacted and made an oxide, so it reacted with oxygen, it would formulate the formula that had there, the Ea2O. The density of the oxide would be about 5.5 grams per centimeter cube, and that it should react with acids and alkalis. Now bear in mind, he made these predictions without ever having seen this element and ever being able to test it. It was just based on what he knew of the elements around it that we knew about at the time. When gallium was discovered in 1875, its properties closely matched those predicted by Mendeleev. So gallium had an atomic mass of 70, a density of 5.9. Its melting point was 29.8 degrees C, which is very low. It formed gallium trioxide, so Ga2O. Its oxide had a density of 5.88 grams per centimeter cubed, and it did react with acids and alkalis. He then also went on to make successful predictions about the properties of the element scandium-45, which was discovered in 1879, germanium-73, which was discovered in 1886, and polonium-209, which was discovered in 1898. None of these elements were present for him to test these things when he made this table, and yet he was able to predict with a great degree of accuracy what their properties were just on this. This was massive at the time. There was a problem, and the problem was one called pair reversal. Mendeleev was looking at his periodic table, and he put the elements in order of increasing atomic number. But this meant that sometimes some elements seemed to be in the wrong group when you compared their properties to other elements in the same group. This is the example, iodine and tellurium. If you look at the periodic table if you look at the table on screen there, I've highlighted iodine and tellurium with the yellow box, and you can see that they go up in order of atomic number. So the element before it, 122, iodine 127, tellurium Te 128. The problem with this is that even though they're in the right mass order, iodine displayed chemical properties that meant it should be in group 7. It should have swapped places with tellurium. Like fluorine, chlorine, and bromine, iodine was a non-metal that does not react easily with oxygen. Tellurium also showed properties that meant it should have been where iodine was, in that it burned in air to form tellurium dioxide, like the other elements in group 6. So Mendeleev swapped them round to match the pattern in the properties. This is important. He did not just sit there and go, well, it must be right because they go in order. He used his observations and placed them around to fit the observed pattern. So this was the new table. He justified this later on to other scientists by saying that actually the mass value for tellurium must not be correct at the time. He couldn't explain it any other way, because if the mass value was adjusted so that tellurium was lower than iodine, this fit perfectly. So that was how Mendeleev predicted the position and properties of unknown elements, and the main problem in his approach, the problem of the pair reversal for iodine and tellurium. Later on, the discovery by Moseley around atomic number helped confirm Mendeleev's ideas, and we're going to explore that now. Explaining the pair reversals then. Scientists continued to work on developing Mendeleev's periodic table after he made his first. In the late 19th century, an entire group of inert or unreactive elements were discovered. Now, these were fit into the table as a whole group on their own because they showed the same chemical properties in that they were completely inert, they were unreactive. Scientists still, though, struggled to explain the pair reversals like tellurium and iodine, because even though Mendeleev had got around it by saying that the masses must have been calculated incorrectly, the repeat measurements of the masses suggested that they were correct. Then, in 1913, Henry Moseley came along and helped clear it up. Moseley's contribution then. He showed that the atomic number of an element is actually a physical property of that element. His actual experiment was to fire high energy X-rays at the element, which made them in turn give off X-rays. Now, if you remember your GCSE physics, you'll know that as an atom absorbs energy, electrons jump, electrons drop, and they re-emit the energy as light. In this case, Moseley discovered for every step change in the atomic number of the element, there was a step change in the energy of the observed X-ray. So if you change the atomic number, even just by 1, the energy of the X-ray that was emitted also changed, which meant that you could link the atomic number to the energy emitted by the element. This was his original graph, or something similar to it, and you can see that for each element, as the element or the atomic number increases, the frequency of the emitted X-ray square root of the frequency also increases. He realized then that the atomic number was equal to the number of positive charges in the nucleus of that atom. The particle that carried this charge, which we know from GCSE science is the proton, was not discovered until a few years later, meaning that the atomic number is the same as the number of positive charges or protons in an elemental atom. So then, how did we arrive at such a universally recognized table? And how then do we know it's correct? Well, in truth, it's through the contributions of many scientists leading to what we have today. What we have today is a new periodic table that's arranged not by mass, but by the atomic or proton number. Elements that exist in a column or group show similar chemical properties to others in the group. So here we've got oxygen, sulfur, selenium, tellurium, polonium, and livermorium. They show similar chemical properties to each other. Elements that exist in a row or period increase in atomic number from left to right. So you can see this is the second period, and from lithium, which has an atomic number of 3, we go to beryllium with an atomic number of 4, over across to boron with an atomic number of 5, carbon 6, nitrogen 7, and just like reading the words on a page in a book, you read from left to right, and the same is true for the periodic table. We go from the left to the right and then drop down to the next period and carry on in that fashion. Another thing, the metals in the periodic table are on the left of the table, with the non-metals existing on the right. The metals make up a large proportion of the periodic table. In fact, if we look at the metals, let's get this here, from lithium all the way across to boron. Boron's a non-metal, but as you go down, boron to silicon, see if I can get this up on here so you can see it. Boron, silicon, germanium, arsenic, antimony. These are where the line blurs between metal and non-metal. All the metals are on this side of the table. The blue section is known as the transition metal element block. Iodine tellurium pair reversal is explained as iodine has a smaller mass, but it has a higher atomic number than tellurium. So what Moseley found out was that even though iodine has a smaller mass, it contains more protons than tellurium. Therefore, its position should be as Mendeleev described in the end, with tellurium coming before iodine in order. So that's the discovery by Moseley around the atomic number that helped confirm Mendeleev's ideas, and also the structure of the modern periodic table that we know and see today.